Sir, wait lang po, may inintay lang.
Hello po, dinig po ba? Hello, good morning everyone.
Yes.
So,
Ah,
we are Group 6. I am Adrian C. Castromero and we will be reporting Chapter 6 Seismic Soil Structure Interaction. So, the magnitude of socioeconomic losses included by an earthquake are heavily influenced by the features of the severe ground motion. It is commonly understood that earthquake ground movements are essentially caused by the three factors: source characteristics, wave propagation path, and local site variables. With the introduction of enormous buildings on soft soils, such as nuclear power plants, concrete, and earth dams, the soil structure interaction or SSI issue has become an essential component of structural engineering, buildings, bridges, tunnels, and subterranean infrastructures. If the structure is very massive and stiff, and the foundation is relatively soft, the motion at the base of the structure may be significantly different than the free field surface motion. For, for code design buildings, it is important to consider the effect of the SSI. A fair assumption is that if a lightweight flexible building is placed on a highly rigid rock foundation, the input motion of the structure's base is the same as the free field seismic motion. The goal of this chapter is to comprehend the fundamental notion of soil-structure interaction by using various methods of analysis with some solved instances. Free field motion and fixed base interaction. Fixed base structure, sorry. Free-field movements are ground motions that are not impacted by the existence of structure. Fixed-base construction are those that are built on rock. When an earthquake strikes a building built on solid rock, the extraordinary high stiffness of the rock constrains the rock motion to be very near to the free field motion. Soil structure interaction. If the structure is supported on soft soil deposit, the foundation's incapacity to adapt to the deformations of the free field motion would lead the motion of the structure's base to diverge from the free field motion. In addition, the dynamic reaction of the structure would cause deformation of the supporting soil. Um, this process in which the response of the soil influence the motion of the structure and the response of the structure influence the motion of soil is referred as SSI as shown in the figure on the report. These impacts are particularly pronounced for stiff and or heavy construction supported on relatively soft soils. These impacts are often minor for soft and or light construction established on rigid soils. It is also crucial for closely spaced structure that may be subjected to pounding when the relative displacement is substantial. For two key reasons, it is vital to have some knowledge of seismic wave propagation in the soil medium in order to adequately grasp the SSI problem. To begin, when seismic waves propagate through the soil as an input ground motion, their dynamic properties are determined by the change of the bedrock motion. Second, when wave propagation analysis is conducted numerically, knowledge of the vibration characteristic of the soil medium is particularly helpful in estimating the soil impedance function and establishing the boundaries of semi-infinite soil. It is critical to comprehend the vocabulary of local site impact in order to understand the influence of local soil condition on the nature of free field ground motion. As a result, in this chapter, the language of local site effect is explained first, followed by presentation of seismic SSI concern. So, terminologies of local site effects. Basin soil effect on the ground motion characteristic. So, first is impedance contrast. So, seismic waves move quicker through hard rocks than through softer rocks and sediments. As the waves travel from tougher to softer rocks, they slow down and must increase in amplitude to transport the same amount of energy. As a result, shaking is more intense in location with weaker surface layers, where seismic waves move more slowly. Impedance contrast is defined as the product of the material's velocity and density. Next, resonance. When the signal frequency matches the fundamental frequency or higher harmonies of the soil layer, they are said to be in resonance. This causes a significant increase in ground motion amplification. Resonance patterns are distinguished by a variety of by spectral peaks. The frequency of these peaks are related to the thickness of velocities of the surface layer. Furthermore, the amplitudes of spectral peaks are mostly connected. The impedance contrast between the superficial layer and underlying bedrock to sediment damping to a somewhat lesser extent to the characteristic of the incident wave field. Basin edge effect. When seismic wave strikes close to the basin's edge, they enter the basin from the edge and proceed in the direction that the basin is thickening. If post-critical incident angles occur, the wave might become trapped within the basin as seen in figure 6.2. Surface waves are generated when trapped waves collide and they propagate throughout the basin. Waves trapped in deep sedimentary basin can have higher amplitudes at intermediate and low frequencies than those recorded on equivalent surface material outside the basins, and their durations can be twice as long. This basin edge effect can magnify long period ground motion components and greatly lengthen the duration of intense shaking. Basin included surface waves cause intense damage which is confined in a narrow strip parallel to the edge. Basement topography. When subjected to body wave incidents below, irregular basement topography causes focusing and defocusing effects. This impact is highly influenced by the azimuth and angle of the incident waves. Trapping waves. Seismic waves are trapped over soft sediments due to the huge impedance differential between the soft sediments and the underlying bedrock. As a result, the length of ground motion increases when the layers are horizontal. This troughing soilly impacts body waves. In the event of lateral heterogeneities, this dropping affects the surface waves as well. The interference of this wave result is resonance pattern. As previously explained, the basin edge effect produces entire reflection of the wave at the layer's base, making them potentially highly harmful. So next,
Okay, hello. Wait lang. So, ano, effect of surface topography. Ay, rinig po ba ako? Hello? Rinig po ako.
Oo, rinig din.
Sige po, thank you po. Effect of surface topography. Surface topography considerably affects the amplitude, the frequency content, and duration of ground motion. So, sa effect of ridge, the ridge generates a large number of surface waves towards the top of the ridge, which propagate towards the ridge's base. The amplification of ground motion is determined by the slope and elevation of the ridge. So, sa effect of the ridge, so dito po sa effect of the ridge, sinasabing ang surface waves ay maaaring sanhi ng structure ng ridges. That way, we can say na ang intensity ng paggalaw ng lupa ay nakabase sa kung gaano kataas or ka-incline ang isang ridge. And we can also say na ang unexpected surface waves na galing sa isang earthquake, particularly po dun sa malalakas na earthquake, ay maaaring maging useful sa pag-locate ng variety of soil properties ng isang shallow structure. Next. effect of valley. It has been numerically predicted that the amplification of the amplitude of motion occurs in the valley owing to the defocusing effect. If valley is devoid of soil deposits, the intensity may be 1 to 2 scales lower than its surrounding area. Next, slope effect. Here, the varying slopes reveal complex damage patterns. Buildings located on or near the bank of steeply sloping hills sustain far more damage than houses located some distance away from the steep slope or on the gentle sloping area in the same hill. Dun sa slope effect, kapag ang slope ay sobrang steep, ibig sabihin, mas nagko-cause ng damage sa mga infrastructures or building kasi nga kapag sobrang steep ng soil, mas greater yung potential for gravity to pull objects down. And mas pwede din siyang mag-cause ng landslide and soil erosions kaysa dun sa gentle sloping areas. Next. Strong lateral discontinuity effect. So sa strong lateral discontinuities are nothing but the areas where a softer material lies besides a more rigid one. The best example of damage caused by strong lateral discontinuity was observed in Batuare Sonar Village during Chamole earthquake noong 1999. The village, situated on a sloping hill at the left bank of river, and the hill mass is composed of rounded pebbles and young soil and is surrounded by hard older quartz rocks. Amplitude application generates local surface waves in the softer medium and larger differential motion caused by shorter wavelength of the surface waves may be the reason behind the greater structural damage. Next na po.
Hello po. Audible po? Audible.
Oo, rinig rin.
Yes po.
So hi guys, I'm Lupango John Michael B. So ang akin ay interaction between ground and structure during earthquake. When an earthquake fault seismic wave E0 hits the bottom of the foundation, it divides into two kinds, as indicated in figure 6.4. Next please. When the transmission wave penetrates a building, it travels in an upward direction, causing the structure to vibrate. They are then reflected at the top and go back down to the structure foundation, denoted by F1. At this stage, the phenomenon of soil-structure interaction occurs. Again, a portion of the wave is transmitted into the earth, while the remainder is reflected back and begins to proceed upwards by the structure depicted as F2. So as you can see in the figure, there's an earthquake fault. Pag nag-trigger, magkakaroon ng seismic wave, denoted as A0. Tapos pag dumama to sa foundation, makahati sa dalawa, E1 and F0. So yung E1, yun yung nararamdaman nating vibration kapag nasa loob tayo ng any structures. Then pupunta yun sa top, pinakataas ng ating structure, then bounce back, pabalik sa lupa. Kapag dumama ulit to sa foundation, mahahati ulit yung waves. Yung iba, mapupunta na sa lupa, then yung iba, babalik ulit. Yun yung mga nararamdaman nating may hina ng paggalaw. Next po. Radiation dumping of the soil refers to the dumping generated by radiation waves. Radiation dumping raises the overall damping of the soil structure system in comparison to the structure itself. Furthermore, when subjected to SSI, the natural frequency of soil structure system must be lower than the natural frequency of the soil. So, anuin muna natin kung ano ba yung damping. So, damping in physics, restraining of vibratory motion. So sila yung parang nagre-restrain ng so siya yung nagre-restrain ng mga movement na yung mga waves natin. So as you can see, kung dun sa base sa figure, ang mga dumping natin dito ay yung foundation saka yung soil. So yung mga radiation wave yung nasa R1 is may hinang mga waves na nagaling sa structure na dumaan sa foundation and also the soil. Next po. So, punta tayo dun sa dalawang interaction kasi meron dito ang dalawang interaction. Una, ang kinematic interaction. Kinematic interaction refers to the SSI effect that is connected with the stiffness of the structure. Because of its flexural stiffness, the massless mat foundation inhibits the vertical movement of the ground motion. As a result, instead of free-filled ground motion, the mat foundation moves differently. That is, the ground motion is away from the foundation. As does not as does the nature of ground motion in the neighborhood and below the foundation. Pasama na nga po. Sumunod. Kinematic interaction occurs whenever the stiffness of the foundation system obstructs the formation of free-field motion. When a foundation is subjected to vertically propagating S-waves with a wavelength to the depth of embedment. The kinematic interaction creates rocking and torsion modes of vibration in the structure that are not represented in free field motion. So, eto based na lang to sa understanding ko na kung ang kinematic interaction ang hinahanap dito is the displacement of the soil. So, pabalik nga doon sa umpisa. Yan. So, yon as you can see, yun yung soil. Kapag nagkakaroon ng movement, di ba, isipin nyo na lang na ano, kuwari nagkaroon ng movement yung soil, kung paano yung movement, ganun din ang galaw ng soil. Pero kapag merong structure, hindi makakagalaw ng ayos ng yung soil. Kumbaga kung ang movement ng soil ay pataas, hindi siya makakamove ng pataas dahil merong structure. Pero ang hinahanap nga lagi doon ay yung displacement lang ng soil. Hindi pa natin sinasama kung ano yung interaction sa structure. Ganun ang kinematic interaction. Pa-next po dun sa So yon, pabalik ulit. Yan yung formula in finding the displacement of the soil. Next po. So, kung sa kinematic ay about lang sa displacement ng soil, dito naman sa inertial interaction, because of the bulk of the structure and foundation, they respond dynamically. Inertial interaction refers to the SSI effect that is connected with the structure's mass. So, kung sa kinematic ay yung displacement ng soil, dito naman sa inertial interaction is yung sa structure na. Kasi meron na siyang mass. Kumbaga, ang hinahanap na natin interaction between the structure, foundation, and also the soil. Yun po. So, sir, pwede pong magpaano po ng video muna bago po ituloy.
Sige, sige.
Ah,
Illustration of solid structure interaction effects. A basic analysis based on Wolff's technique illustrates the solid structure interaction. Consider the mass, stiffness, and damping coefficient of a single degree of freedom system, coupled to a massless rigid, L-shaped foundation of height as shown in figure 6.9, yung nasa figure sa baba. A horizontal amplitude stimulation is applied to the system. The natural frequency of the resulting fixed base system will be if the material supporting the foundation is stiff. The foundation can translate and rotate if the supporting material is compatible. The stiffness and damping characteristics of the compliant soil foundation system are presented by Kh and Ch in the horizontal direction and in the rotational direction. Direct method. The soil structure and foundation are all modeled simultaneous, simultaneously using the finite element method and examined in a single step in the direct approach. The ground motion is defined as free field motion and is applied to all boundaries.
Substructure method. It is computationally more efficient than the direct method as most of the disadvantages of the direct method can be removed if the substructure method is employed. In this method, the effective input in motion is expressed in terms of free field motion of the soil layer initially. Means substructure method is an established way of overcoming the difficulty of large dimensionality in analysis structures. An improved substructure analysis method suitable for structures like stored buildings and towers is presented in this paper. This picture daw po ay represent represent yung substructure method ng roof, second floor, and ground floor. Sa substructure naman po ay foundation. Take note that in case of soil or foundation medium modeling of some structures, a portion of the soil may be included in the superstructure as shown in this figure. Figure A represent STOF or single degree of freedom system resting on a half face. Figure B represent modeling superstructure and soil medium separately. And figure C represents some portion of the soil included in the superstructure model. For such structures, two interfaces exist, one at the free ground surface and the other at the surface between the superstructure and the soil or foundation medium. The superstructure method of analysis can be explained in detail with STOF structure supported by a rigid foundation slab resting on an elastic half face. Consider a SDOF system supported on a rigid base of a mass and mass moment of inertia, resting on a half space as shown in figure. A. To make the tau effect negligible, the horizontal dimensions of the base are assumed as sufficient small. The uniform field ground acceleration at the field surface will introduce the foundation forces at the interface between the base of the structure and the half space. B. It is also assumed that a rigid massless plate is present on the surface of the half space to ensure its displacement compatibility with the lower surface of the rigid base. The total base displacement of the SDOF system shown in figure will be V raised to T times T is equal to U sub G times T plus V times T, where U sub G times T is equal to free field ground displacement. V times T is equal to added displacement or base displacement caused by SSI. Also, theta times T represents the base rotation caused by SSI. It is also noted that as the SSI results in translation and rotation of the base of SDOF system, It is introduces and displacement of the system, and thus the overall system has 3 DOF. MDOF, or multi-degree of freedom system, will with multi-support excitation considering SSI. The basic principles involved in the analysis of SDOF system are same and applicable for the MDOF system, except that the formulation of the equation in case of MDOF system with multi-support excitation is more complex. MDOF system with multi-support excitation considering SSI. Equation U raised to T is equals to U plus U sub Y plus U sub D, where U raised to T is equals to total or absolute displacement of the system from a fixed reference. U is equal to the vector of the displacements produced at all non-supported degrees of freedom produced due to the ground displacements at the supports. U sub Y, the vector of the displacement at the support for maintaining elastic compatibility between the foundation and the soil. U sub D is equal to the vector of the relative dynamic displacements produced at all non-supportive degrees of freedom due to the inertial actions. Seismic SSI with substructure method. A represent MDOF system with multi-support excitation. B represent modeling superstructure substructure number 1 and soil medium. Example substructure number 2 separately. And C represents some portion of the soil is included in the superstructure model referred as substructure number 1 and remaining soil as substructure number 2. Solution of SSI problem using Abacus software. The SSI problem can be solved using Abacus software by following the steps mentioned below. Step 1. Part module. Forming the geometry of the structure and soil. Step 2. Property module. Generating the property of the structure and soil. Step 3. Assembly module. Assembly of the structure and soil into a common platform. Step 3. Step 4. Step module. Define the analysis type. Step 5. Interaction module. Define the interaction between the structure and soil medium. Step C. BC module. Define the boundary condition in the structure. Step 7. Mesh module. Meshing of the structure and soil. Step 8. Job module. Submission of the job for the analysis. Step 9. Visualization module. Viewing the results. Thank you po. Reported by Jonathan Patidungan.
May quiz din po ako.